So this program of getting finite results out of a perturbation theory which is seemingly divergent, I mean it's each element is diverging in ultraviolet. Okay, that program is called renormalization. So there are two steps involved in this. The step number one is to introduce a regulator, okay, whose job is to make the integrals finite. So you introduce a regulator, the integral then depends on that regulator, it becomes a function of that regulator. And the purpose of that regulator is to make the integral finite, okay, in ultraviolet. But of course, if you were to remove the regulator, it will become divergent again, and we need to remove the regulator. So introduce a regulator to make the integrals UV finite. Okay, and this procedure is called regularization. For example, we have already seen one example. Okay, too many examples in the same sentence, not nice. So one regularization method we have seen, and that is cutoff. Okay, so here you introduce a cutoff and say that I will cut off the integrals at some momentum value, high momentum value lambda. Okay, so now your integrals will depend on this cutoff, right? Because there is lambda. But our real thing is when lambda goes to infinity. So at the end, I have to take lambda going to infinity. So it looks like this is not going to help, which is true. Having just a regulator is not going to help. Something else has to do the magic so that we get finite results. Okay, and that magic is called renormalization. And I will tell you in more detail how that thing works. So the idea is you introduce this cutoff and calculate whatever observable you want to calculate with the cutoff in place, and your result will depend on the cutoff. Okay, but we'll see that we can arrange things in a manner that these divergences which are appearing, which will appear as function of lambda, right? Because lambda is to filter out the divergences. So within that observable, we will be able to cancel the ultraviolet divergences. So all the divergences which are functions of lambda, they will cancel. And then once the divergences have cancelled, we are free to take lambda going to infinity. Okay, and our result will still remain finite. Okay, and that is what is called renormalization. Okay, this procedure of subtracting infinities. So I will talk about different ways, different methods of regularization first, and then we'll move on to renormalization. But here's something I want to point out based on what we have already seen here. So how many parameters do we have in this action? We have two parameters, m and lambda. Okay, and let's look at one loop. We'll worry about higher loops later, but if you look at one loop, then this 2-point function is divergent because of this diagram. Okay, that's one diagram which is divergent. At or one 2-point Green function which is divergent at one loop. Then you have another one. Where did that go? Here. This one, 4-point function, which is also divergent at one loop. Right? So you have two Green's functions which are divergent at one loop. But when we went to higher order Green's functions, like this one, this is not divergent at one loop. Right? This one is not divergent. And you can imagine drawing other one loop diagrams that will be just introducing more vertices, so you get higher point functions, and they will also not be divergent. So two Green's functions which are divergent at one loop, and you have two parameters m and lambda in the theory which are not physical quantities. So you never measure m, you never measure lambda. These are not physical objects. Right? What you measure is a physical mass. You can measure the mass of an electron. Okay? Or you can measure the strength of the interaction of one electron with another electron. Okay? These are the things you can measure. You can measure cross sections. But there is nothing you can do to measure m and lambda. So right now the situation is that you have two parameters which are not measurable, and you have two Green's functions at one loop which are divergent. And what one does is hides these infinities which you are seeing at one loop in these two parameters. Okay, and then you can get a result that is finite up to one loop. Okay, and we'll see how this can also why this will work at two similar things will work at two loop also. But roughly that is the thing, and I will tell you in detail later how to do these steps to get a finite cross section. But before that, I want to I want to look at the ultraviolet divergences in all these Feynman diagrams a bit more carefully, as I have been saying repeatedly that I will do it later. So now let's do that part. And we can see that ultraviolet divergences become very transparent if we do if we do a Wick rotation, both in the loop momentum and the external momentum. Okay, so that's what I'm going to do. And when we go to the physical external momentum, okay, so we have gone to, I'm saying these steps, let me remind you. Just a second. Yeah. Yeah, here for example, or even earlier. Here. So when we were doing this integral, we had gone to p square, which was the external momentum, p square, that small p square. We made it space-like, which is not the physical region, okay, which you can also do by taking the 0th component of p to be imaginary, okay, then p square will become negative. And here we had done a Wick rotation so that we got this denominator, okay. This integral was well defined. Here it is, once you have done this, here it is easy to see the ultraviolet divergence, because now everything is adding up. It's not unlike the previous case where k0 square minus k vector square, you had a minus sign, and no, it's not so clear what kind of divergences you are getting, okay, because if you take all k0 and k1, k2, k3 all to be of the same order, then you can get cancellations between k0 square minus these other terms. Okay. So, but here it is all very clean because there is no cancellation between different components. So here you see that in this case you have two powers in the numerator. So both k1 and k2 are large. Let's say you've put a cutoff lambda. So for both of them you have a cutoff lambda. So two powers here, and then you have two powers here, and that's squared. Okay. So 4 and 2 here. So this is convergent, and this is convergent because we had gone to 2 dimensions, right? This integral we evaluated in 2 dimensions. So that's what we want to do again. And the lesson from here, I'm going to rewrite this thing, okay, in the following way. Okay, as I said, I will take the external momenta, which are pi's, okay, and I will rotate them. Okay, I'm thinking of doing integrals in n dimension. Okay, for at this moment it's not clear why I'm doing this, why I want to be in n dimensions. Okay, but let's say that for whatever reasons I want to work instead of 4 in n dimensions. Okay, but if you don't like it, you can put n equal to 4. There is nothing is going to change in the reasoning. Okay, so this and also the loop momenta we had done this. Okay, so that's the Wick rotation, and we just saw that thing in the red box, that if you look at this 2-point function and do the integral, okay, then it is of the following form: integral 0 to 1 dx integral. So that was 2 dimensions, but I'm saying n dimensions now, and then that was in the Euclidean space. So I call the loop momentum vector as k e for the Euclidean. Okay, and here similarly you will have 2 pi to the n, and this vector of minus k e square minus m square whole square. Let's go back and check whether indeed we have the same form. Here you see, this is, so let's bring the minus sign inside. I had taken it out, but let's put it back. So there's square, so that minus goes in here and it multiplies everything. Okay, so it is minus of this square minus that square, which is minus of k Euclidean square, that's the definition. Then minus this object is positive, so minus of a positive object, because x is positive and 1 minus x will always be positive because x lies between 0 and 1, and p square was space-like, okay, because it is Wick rotated, and that is what we are. So this is minus this positive object minus m square, okay, because of that minus sign. So it becomes negative of a positive quantity, and that is what I am writing as capital M square. Okay, so that's the form, and I have dropped I epsilon because there is no need for it when we are in the Euclidean space. Okay, and here m square is a function of x, p square and m square. now we can very cleanly see what is the degree of divergence. So I have this integral. See, the x integrals are not going to give you any ultraviolet divergence. They run from 0 to 1. They don't go to infinity. Okay, so that's not going to give ultraviolet divergences. They give rise to something called infrared divergences, but right now we are not concerned with any infrared divergences. Okay, infrared or collinear divergences, they give in theories where you have massless particles, but they cannot give rise to any ultraviolet divergences. Okay, so ultraviolet divergences are completely contained in this. And as I said, that going to the physical external momenta, okay, and going back to the real axis, that is not going to generate any ultraviolet divergences, any additional things. So whatever ultraviolet divergence is contained in these weak rotated integrals is the real ultraviolet divergence. Okay, and that's why I am showing you these integrals. So from here now we can estimate what is the degree of divergence. Okay, so I hope it is clear, but if not, then you should do a radial integral and an angular integral. Okay, this is a vector Ke in n-dimensional Euclidean space. For example, n could be 2, so it's a vector Ke in this 2-dimensional space. Okay, you can do integral by integrating this way. So as you go out, you are integrating over the radius or the magnitude of the vector r, and the other integral will involve integrating over angle which is theta. Okay, so these two integrals are in theta, and the generalization of this for n dimensions you have to do. Okay, now angular integrals do not give any divergence, any ultraviolet divergence. Okay, these angular integrals have finite volume. Like here it is theta goes from 0 to 2 pi. Okay, that's something finite. If it was sphere, then the solid angle will be 4 pi and so forth. That doesn't give you any infinity. Okay, what gives you infinity is because this radius goes to infinity. Okay, so that is the source. So we can just forget about the angular integrals also and just worry about the radial integral. Okay. Okay. So suppressing the angular part, let's look at the radial part. So radial part will be integral 0 to infinity. Okay, you will have r to the n minus 1 dr, and that makes n powers of momenta, right? Dr has 1 power of momentum, and r power n minus 1 has n minus 1 powers. So together n powers, and this is anyway minus r square power 2. I have dropped m square because m square is something finite, right? P square you have chosen, that's something given to you by your process. Okay, m square is finite, this is finite, x ranges from 0 to 1, that's finite. So as r becomes large, m square you can drop in comparison with large r. Okay, and then you see the divergence is like this. If when n minus 1 so you I hope everything is, we are doing for this specific integral. So when n minus 1 minus 4, okay, is for here, and -4 should be less than 1. Okay, because n minus 1 minus 4, let's say if it is equal to 1, no, not 1, no, should be less than -1. So if n minus 1 minus 4 is, let's say 0, okay, let's say 0, then you have what am I doing? dr 0, yeah, then it is divergent, right? Because then you have just integral dr, okay, because there will be no power of r coming from this, because n minus 1 minus 4 is 0. Okay, so that will be divergent. Then even if you had a power of r in the denominator, which is r minus 1, that would also be divergent, and that is why n minus 1 minus 4 should be less than -1. Okay, or n minus should be less than -1. Okay, so fine. This is fine. Then what next? Yeah. Then we have also looked at the general multi-loop integral earlier, which is here, right? That's the, let me remind you. Yeah. So we were looking at this Feynman integral, and you see here we had n propagators, and for each propagator we had nx1, nxi. So that is why you have n number of Feynman parameters, and that's the delta function. I think this is something I inserted today. I had forgotten in the previous video. And then you had this denominator. Okay, and these are the loop momenta, which are still in the Minkowski space. Then I did a Wick rotation. Okay, and after doing a Wick rotation, this is the denominator, where L0, you see here, Li0 is Lin times e to the I pi by 2, which is I, right? So here, that's the denominator, where here I should put a e to the 2I pi by 2, okay, which is going to give you -1, okay. And I had suppressed the labels on x, so this is what we had in the denominator. Okay, so let's look at this one and try to carefully find out the degree of divergence for such diagrams. Okay, and this time I'm doing properly in the Euclidean space. Just like for this diagram.